Da da da, Science Today Show.
Welcome, ladies and gentlemen, to the Science Today Show. I'm your host, James Jewell, and today we are going to be interviewing Dr. Maxwell. So, Dr. Maxwell, you are a physicist at the University of Colorado?
Yes, that is correct. I've been working there for the past 15 years.
Very interesting. Many calculus students often wonder where are they going to use calculus in their area of study. Would you please enlighten us on how you use calculus in your field?
Certainly. Mathematics is fundamental in my field of study. It is used both to represent and to explain physical phenomena, such as motion. To answer your question, calculus is used extensively in deriving some of these laws and theories. One very interesting example of this is the kinetic molecular theory, which connects pressure and temperature to energy.
That sounds very interesting. Can you please tell us more on this topic?
Of course. Kinetic molecular theory states that temperature and pressure are both manifestations of energy. Therefore, I will try to derive a mathematical relationship that shows how pressure is related to energy and how temperature is related to energy. I will first show how pressure is related to energy. This will make more sense towards the end of the video. To begin, I have to explain what pressure is. Pressure is force over a certain area. In our example, this force will be caused by the change in momentum of each molecule over the total area. So, first, we have to describe how these molecules are colliding with the wall. Let us consider the situation shown here, where we have a certain n number of molecules and a volume adjacent to a wall with an area A. Each of these molecules has a random velocity, but we need to be concerned with those molecules with a specific velocity. I'm going to say that this specific velocity is between u and u plus du, where u is the velocity and du is a small change in this velocity. I'm going to say that these molecules are dn. This is because dn is just a small proportion of the total number of molecules n. Therefore, the fraction of these molecules over the total can be represented as dn over n. This will be equal to some density function, Fu, times du. The actual expression for Fu is unimportant at this time and too complicated to explain. Therefore, we can figure out now what these numbers of molecules are by multiplying this side by n and this side by n to get dn equal to n times Fu du. Now, we're concerned with those molecules per unit volume of the total volume. So these molecules, dn, over the total volume V. We already know what dn is, NFUD. So if we replace this here, we'll obtain the expression n over V times Fu du. Now, these molecules in a certain time dt will collide with the surface, where dt is just simply a change in time. So the volume that these molecules go through can be represented by the area times the distance that they go through. This distance will be u dt. That is because each of those molecules has a velocity of at least u, and they go through a certain time dt. U is velocity, or change in distance over change in time. So if we take this change in distance over change in time times time, we will obtain the distance, and therefore this is a length. So now if we take this length times the area, we will get the volume that these molecules go through, or in other words, AU dt. Now if we take this volume times the expression we obtained here, we get the amount of molecules that collide per volume, which is N over V times FU AU du dt. Now, each of these molecules undergo a certain change in momentum. Momentum is mass times velocity. Since these are the same element, the mass will be the same for each molecule. Therefore, each of these molecules will undergo some change in momentum to mu, because at first they have a momentum of mu, and when they hit the wall and come back, they will have a momentum of negative mu. So the change will be 2 mu. Now this is per molecule. So the momentum caused per molecule can be represented as this: dp, or change in momentum, equal to 2 mu n over v fu au du dt. Now if we simplify that equation, we will get 2 mu squared n over v fu au du dt. Now we're looking for the pressure. So the pressure caused per molecule is the change in momentum over time over the total area, as shown here. Now we already shown that dp is equal to this. So when we take that over the time and over area, we will obtain this expression, which simplifies to 2 times mu squared n over v fu du. Now that's per molecule. If we want the total pressure, we need to integrate both sides. So the integral of dp is equal to 2 mn over v, because these are all constants, times the integral from 0 to infinity u squared fu du. Now the reason the bound is between 0 and infinity is because the integral is with respect to velocity, and we're only concerned with velocities that are positive. Now, with respect to the density function, from negative infinity to positive infinity of u squared fu du, this will be the mean velocity squared in the x direction, as this is all in the x direction. Since from negative infinity to 0, or the negative velocities, come out with the same as the positive velocities from 0 to positive infinity, this will be equal to 2 times this. Now, let's take the expression we obtained here and replace 2 integral 0 to infinity u squared fu du with mean velocity squared of the x direction. We will then obtain p equal to m times n times mean velocity squared over volume. Now, since this is in the x direction, each of these molecules actually has a velocity in the x direction, y direction, and the z direction. I'm going to say that in the x direction, it's u squared. In the y direction, it will be v. And in the z direction, it will be w. Therefore, if we want what the total mean speed squared is, we know that the direction that the molecules is going in doesn't really matter. Therefore, the mean velocity squared in the x direction is the same as the mean velocity squared in the y direction, which is the mean velocity squared in the z direction. Therefore, that's equal to the mean speed squared over 3. Now let's replace that in our equation. We will then obtain PV, if we multiply V to the other side, equal to m and mean speed squared over 3. Now in physics, we know that kinetic energy is 1/2 m times mean speed squared. If we want the total energy, because the m is only for each individual molecule, we'll have to multiply that by m. So now let's take our expression here and divide by 2 and multiply by 3 to obtain this. Notice that this is equal to the kinetic energy. Therefore, 3/2 PV is equal to kinetic energy. Now if we rearrange that equation so it's equal to P, we have P equal to 2/3 energy over volume. This shows how pressure is a function of energy. Now in relation to temperature, what we have here is an ideal gas. Therefore, it follows the ideal gas law. PV equals to nRT, where P is pressure, V is volume, N is the number of moles, which is the amount of gas, R is some gas constant, and T is temperature. Well, we already know that PV is equal to 2/3 EK by a little manipulation. Therefore, since PV is also equal to nRT, we can do some rearrangement so that nRT is equal to 2/3 times energy. Now let's solve for T. We will obtain temperature equal to 2/3 energy over N times R. Therefore, that shows that temperature is a function of energy. Therefore, we have derived a mathematical relationship that shows that pressure is a function of energy and temperature is a function of energy. In this deriving process, we used calculus. This shows how we use calculus in our field of study.
Wow, that was an interesting presentation. Thank you, Dr. Maxwell, for coming on the show and explaining to us this kinetic molecular theory. Thank you, ladies and gentlemen, for watching our show, and we hope you see you next time on the Science Today show.